Day 2 will look at paper cutting and geometric sequences. Take a look at the 4 sequences below. What do you notice? What do you wonder? So sequences is this ordered list of numbers that follows a pattern. So in the first one, we have to figure out, we know they're increasing, but by how much? So for this one, if you divide 120 by 40, it looks like it's going up by 3 every time, and that works for all of them. In our second one, it looks like it's increasing by a multiple of 4. In our third one, it's going down, but by a factor of half. So we're multiplying by half every time. In our last one, I wasn't sure, so I divided. I did 192 divided by the number before it, 256, and I got 0.75. And then if I try that with another one, like 81 divided by 108, you get the same thing. So again, if we take any number and divide by the number before it, we get this, it's called a ratio, so it's what we're multiplying by each time. So here it's by 0.75. So in all of these, they're being multiplied by the same number every time to get to the next term. All right, so our task today, Faiza takes a piece of paper, cuts it in half, and then stacks the pieces. She takes the stack of 2 pieces and then cuts them in half again to form 4 pieces, stacking them, cutting them in half, and repeating the process. The original paper has a length of 8 inches by 10 inches. Okay, so let's write that down, 8 by 10. All right, so if there's 0 cuts, it's 1 piece. In the areas of a rectangle is base times height, so that's 80 square inches. So then we're going to cut it in half. There's 2 ways we can cut it, and let's see if it makes a difference. So let's cut it this way first, and if we cut it this way, then each paper would be 8 by 5. 8 by 5, which is 40, and there's 2 pieces. What if we cut it this way? So if we cut it this way, half of 8 is 4, half of 10, no, 10 we keep the same, so that would be the same thing. It's still 40, and there's still 2 pieces. Okay, so that works. Let's cut it in half again. So we would stack them and cut it like this way. So if we did that, this side would be 4, this side would be 5. 4 times 5 is 20, and there's 4 pieces. If we did that over here, would it be the same? So let's cut it. Let's try cutting it this way. This would be 2 by 10, and that's still 20. So does it matter which way we cut it? It looks like no, it doesn't. Our numbers end up still being the same. All right, so then we have to cut them in half again. So it's this green piece that I'm going to cut in half again. So imagine cutting all of these in half. So we have 8 pieces. And each piece is 4 by half of 5, so 2.5. So 2.5 times 4, which is 10. Okay, let's cut it in half again. So we have 16 pieces now. So if we look at this, this would be 2 by 2.5, which would be 5. And you can kind of guess what the next one's going to be. So we'll draw our last one up here. Cut it in half this way. So this is 2 by, I don't know what half of 2.5 is. It's 1.25. So 1.25 times 2, which is 2.5, which is half of 5, and there will be 32 pieces. Describe in words how you can use the results after 5 cuts to find the results after 6 cuts. So the number of pieces you can multiply by 2. So multiply the output number of pieces by 2. But over here, you take this area, so you take half of the area. So divide it by 2. So we're multiplying this one by 2, but we're dividing this one by 2. On the given axis, sketch a graph of the number of pieces as a function of the number of cuts. How can you see on this graph how the number of pieces is changing with each cuts? Okay, so this is number of cuts, which we don't have a table for. Oh, but it's right here. Oh, okay, number of pieces, number of cuts. Okay, so we're looking at these 2 parts of the table, which is funny because usually we put the x, the independent variable, first, and they're kind of reversing it. Okay, so when there's 1 cut, there's 0 pieces. When there's 2 cuts, there's 1 piece. When there's 4 cuts, there's 2 pieces. Okay, so 2, 1, 4, 2. I mean, going up a little bit. When there's 8 cuts, there's 3 pieces. Wait, am I doing this right? So number of cuts. Oh no, that was right. Sorry, I was wrong. I was graphing it the wrong way. So the table is in the right order. So number of cuts is on the bottom and number of pieces is here. Okay, so sorry. We'll do it again. So when there's 0 cuts, there's 1 piece. It's like right here. When there's 1 cut, there's 2 pieces. 2 cuts, there's 4 pieces. 3 cuts, there's 8. 4 cuts, there's 16. 5 cuts, there's 32. Okay, so that was, the table was in the right order. Okay, there's our graph. How is it changing? It says given, okay. How can you see on the graph how the number of pieces is changing with each cut? Okay, so we can see that it's, from the table we can see it's doubling. Can you very easily see that from the graph? I would say not as much, but you can see it's exponential. On the given axis, sketch a graph of the area of each piece as a function of the number of cuts. Okay, so we're looking at this column right here and this column right here. So 0, 80 is the first dot. 0, 80. Okay. 140 is the next one. 240. No, wait, did I do that right? 244. Okay. 0, 80, 140, 220. 3 is 10. 4 is 5. 5 is 2.5. Okay. All right, so we can see this as like exponential decay right here. How can you see how the area is changing? So it's going down by half every time. Faiza has a piece of paper that's 8 by 10, so same piece of paper. How many pieces of paper will Faiza have if she cuts the paper in half n times? Okay, so let's think about what it's asking. Pieces of paper n times. What will the area of each piece be? So we have to see how these are related. Okay, so how many pieces? So n is the number of cuts. So the number of pieces. So one way to look at it is this is 2 to the 0 power, 2 to the first power, 2 squared, 2 to the third, 2 to the fourth. So 2 to the n will be the number of pieces. Okay, how many pieces of paper? 2 to the n. Okay, so that was the pattern. Okay, but how about this? What will the area be? Okay, so we have to take a look at how these numbers correspond to these numbers right here. So it's going down, so this will be like dividing by 2 every time, but 80 divided by 2, 80 divided by 2, and then 2 again, so 80 divided by 4, 80 divided by 8, 80 divided by, okay. So I think what's happening is area. It looks like it's 80 divided by 2 to the n. So let's try that. So when it's 0, 2 to the 0 is 1, so that works. So how about the next one? 80 divided by 2 to the first power. Okay, yeah, that works. How about 80 divided by 2 squared? That works. Oops, I went too far. We should try this one. 80 divided by 2 to the fourth power. Does that give us 5? 80 divided by 2. Let me put this in parentheses here. I'm just typing my calculator. To the fourth power. Yep, that works. Okay, so here's our function. It's 80 divided by 2 to the n for the area. Why is the product of the number of pieces and the area always the same? Oh, because if we multiply them, take a look at what happens. 2 to the n times 80 over 2 to the n. These will cancel and we'll always get 80. So if you're, what it's saying is if you're multiplying, I'm running out of colors here, we'll do orange. If we multiply the number of pieces by this, we'll get the same number every time. And the reason is this is going up by the same amount this is going down. Again, if you look at your pattern here, it's easier to see that this is 2 to the n, this is 80 divided by 2 to the n, the 2 to the n's would cancel and you get 80 every time. So our summary here is, what is a geometric sequence? It's a sequence created by, it's a list of numbers that to get to the next number you multiply by the same number every time. So geometric sequence, multiply by the same number to get the next number. And that number that you're multiplying by is called the common ratio. The number you multiply by to get the next number. Okay, so here's an example. Complete each geometric sequence. We got to figure out what is this going up by every time. And if it says it's geometric, it's really easy to figure out the common ratio. You just take any number and divide by the one before. So 6 divided by 3 is 2. You could even do 3 divided by 1.5 and you'll get 2. So this is multiplying by 2 every time. So this will be 12 and this will be 48. All right, let's go over here. Again, if we want the ratio, just take any number, divide by the number before it. So this is 3. We're multiplying by 3 every time. All right, so we'll do 360 times 3. We'll get 1080 and then 3,240. All right, over here it's going down, but again, if you want to figure out what number we'll multiply, just pick any number, divide by the one before it, which is 1/10 or 0.1. Let's double check. Okay, so to get the next number, we're just multiplying by 0.1 every time, or by 1/10. So 2 times 0.1 is 0.2. Do it again, and that's 0.02. Okay, this one is multiplying by 0.5 every time. In this one right here, again, how do we find what is being multiplied by? So just take any number, divide by the one before it. If you divide by fractions, it's the same as multiplying by the reciprocal. So these cancel, whoopsies. And when you multiply fractions, you go straight across, so 27 over 9 is 3. So this is multiplying by 3 every time. So this will be 3 over 7. Let's change colors. 9 over 7, 27 over 7. So really we're just multiplying the top by 3, the numerator. So this will be 81 over 7. Okay? With your group, come up with a geometric sequence, share it with the class. Is this a geometric sequence? You could argue yes. The common ratio is 1. We're multiplying by 1 every time. All right, so your assignment then is to do the daily practice for day 2. Looks like it goes from pages 6 to pages 7. Pages 6 to 7.